first, and the others are colleagues of university and the IMR. Okay. Okay, that was a brief talk. There it is. Okay, so as I mentioned, there are a number of issues. I could start raising my flag in my hand already on the outline, because the problem of this whether we have systems with alternative equilibria in the Arctic, it's already something to raise our hands upon, because the hard evidence is not there yet. So we don't have experimental evidence that there are alternative equilibria in the communities we study. The problem of resilience is worth raising hands on, because now management has to deal in the near future, ecosystem-based management with the resilience, and we don't have neither the tools, we don't have the theory, and we certainly don't have management options that are targeting the problem of resilience. So even the concept of resilience is problematic. So second point we can discuss together. And then comes the real issue. I mean, mechanisms of bistability, that is theory. If we have tipping points in the Arctic, if we are risking in a setting which environmental change is affecting our communities, our ecosystems, if that's the situation, then we should have some ideas of what are the mechanisms, so the biological mechanisms behind these tipping points, in order to have some predictions, some expectations, in order to direct, again, management action. Without that, without the theory, we are don't have many options open to us. And typically, theoreticians, when you're dealing with a problem like environmental change and what to do with it, scientists say we are unfortunately ignorant, still very ignorant about what's going on in the Arctic. But the theoretician will tell you we lack the theory. The empiricist will tell you we lack the facts. And the real story is that we lack both. But you need the theory if you want to gather the facts that are relevant to the problem. Okay, so we do have to deal with that problem anyway. So managing and tipping points, that's a big issue. That's something that is coming. It's going to relate to resilience. The problem of resilience is going to relate to the problem of alternative stable states. And it's going to deal very much within natural communities with food webs. So with essentially with the relationships between the organisms in our communities. I've heard that several of you are dealing with food webs, mapping food webs, analyzing food webs. Okay, that's a big task. It's the ones of you who are dealing with that know how much effort goes into just finding out who is eating who within a community. Okay, and once the task is done, you're left with the question. Okay, now I should move on, and what is the next step? In terms of finding out whether you have tipping points, the next step is to find out whether some of the species are involved in type of relationships or in type of interactions that can give rise to alternative equilibrium and tipping points. So that's the one step that we need to deal with, which has to do with mechanisms of bistability.
Raul, sorry, may I interrupt briefly?
Yeah, we'll take it.
Can you just clarify with bistability? That's a term that I haven't heard yet.
Okay, so we said already there are a number of definitions that we will deal with today. Bistability is what we're going to model today, and that essentially refers to a system like, for example, a fish population that has a certain abundance. And a bistable fish population is essentially a population of fish that can have two alternative states. For example, an overcrowded one with many fish in a lake or in a fjord, or a low equilibrium abundance, for example. And there are both equilibrium. That means that population, if it reaches a low equilibrium, it can stay there for a very long time. Okay? So bistable, two stable equilibrium. Okay, and the question is whether anything like that exists. So that's something we should ask, because if it does exist, then we have a tipping point, and that's the issue of our talk. Okay, so the problem of strong evidence essentially is dealing with what we're suggesting now. Do we have anything like that? Do we have any fish population that has alternative abundances, alternative equilibrium abundances? The second issue is one of what mechanisms may underlie that type of bistability. And the third is, can we devise management options to deal with the tipping points that characterize that particular population or community? Okay. Well, if we want to look for evidence in this type of the issues, so evidence of bistability plus information about mechanisms plus management options. We found out that if you review the studies that deal with tipping points and management, okay, and you do it at least in 2009, there was for the Arctic only one study, one single study that took all the three steps there, and the study was conducted in a Lake Lofoten, which is close to Tromso. Okay, so I know about the study because I was involved as a PhD student and a postdoc. But the ones that led the study were Anders Clemmensen, and then Per-Arne Amundsen, and some of the other co-authors. Lennart Persson is a colleague in Umeå, and Andre de Ros is the theoretician, so the guy that developed the models. And this collaboration is a collaboration between empiricists, theoreticians, and in an attempt to deal with the management issues raised by this bistability, or alternative stable states, or tipping points. Okay. So the experiment was a simple one. There was a overcrowded population of char. There was a need to reduce the abundance of the fish and try to obtain a low equilibrium abundance. Somehow try to push the fish population down to just fewer individuals in the lake, because when the fish population is overcrowded, it tends to the fish tends to become stunted. They grow just to a very small size. They become very heavily parasitized, and they are no longer interesting for the fishermen or for the people that might exploit that resource. So there is a management problem. You don't want to have overcrowded lakes. Many lakes in Scandinavia are overcrowded, and they become overcrowded after overfishing. So after a period of, you may say, flawed exploitation. Okay. So that's a problem. And what happened in this lake was that there was a fish removal. That's the experiment, if you wish. There was an overcrowded population with lots of individuals. They removed 660,000 fish, and look at what happened. There was a rebound. The population increased for a period, then went up and down, and now it's stabilized, and it's still there in 2010 at a lower equilibrium. That's an experimental approach. You have a perturbation showing that you have two alternative equilibria for the char population of Lake Lofoten. Okay, we know that you need this type of manipulation in a short term in order to have the conditions to show empirically that there is a bistability. The way we represent it, and one way to represent this situation is that you show the overcrowded state as one cup, okay, then you have your marble, and then you have the alternative state as a new equilibrium, that's the low equilibrium abundance, with just few fish that are big and grow well and are not parasitized and all that. So the manager would want to have this state, and the problem is, how can I reach that state? So what is the management option? Well, one idea is, what they did was fish out the animal, eliminate a lot of char, and try to reach that particular point. The problem is that a priori, if you don't have a model, if you don't have an understanding of the system, you have no idea how many fish you should fish out. You don't know whether you should fish out all the animals, you should target only the large, only the small. You have no idea where to move, okay? And the one issue for the manager is really, how far down should I push it, okay? That's a big effort involved in fishing out 660,000 animals from the lake. So there is a problem of understanding where the tipping point is, which relates to resilience, which is the other concept that we need in ecosystem-based management. Okay, and I'll show you how it relates to it. If we assume that the tipping point is there, then we have a certain effort shown that by the arrow. So I do my fishing experiment, I try to tip over the system, and it does work. Okay, I was lucky. I didn't know a priori. I didn't have any explanatory, any framework to devise such a management action. Okay, but I did add at the time in the 18th some expectation that there would be two alternative equilibria in the lake. Okay, so that was the situation. The problem is, I didn't know where the tipping point was. If the tipping point had been further away, so if the equilibrium, okay, this equilibrium state, the overcrowded state, had a higher resilience, that means I needed to perturb more to flip the system over to the low equilibrium state. Okay, if that was the situation, my attempt here might have been might have failed. Okay, so that was the problem. We didn't know the resilience of the overcrowded state. And we didn't know at the time. I wasn't, I think at this time I was about 12 years old, so it wasn't probably even a thought in my mind. But Anders, Clemensen, and Perane, they definitely had an issue there. And they wanted to know, they had to know, should we target all the fish and how much should we fish, okay? They introduced sort of traps in the lake so that they catch both the juvenile and the large individuals. They caught a lot of small individuals from the lake. And that turned out, a posteriori, later on when the theory was developed, pretty much in this period of time, okay, when we finally had the mechanism for the bistability in the lake, okay, it turned out that that was the correct management action. You should target the small, so the juvenile fish, rather than the adults, if you want to have a successful management action. Okay, so if we have a higher stability, that would require more effort. If you want to have a targeted effort, you need the theory, you need the understanding. Here is a simple model that accounts for the stability that we are going to work with. You're going to try the simulation, see whether a population of trout that consists of juvenile and adults, in which the juvenile will essentially they grow to maturity. Okay, that's the blue line shows the transition rate to maturity, and then the adults recruit the juveniles. And there is something important in terms of generating the conditions for the tipping point and bistability, and that is what they call the feedback structure. Essentially, the transition rate, so this rate of transition from juvenile to adult, is affected by competition among the juveniles for plankton. So the juvenile compete between each other, so among them, but they do not compete with the adults, which feed in a different area on larger prey. Okay, so there is competition within the stage of the juveniles, affecting transition rate, so they mature later if there is a lot of competition, and then there is competition within the adult stage for their own large prey, but there is no between stage competition. That's the condition that we need in order to generate bistability. This condition arises whenever you have, for example, a fish that changes its diet and its habitat throughout its life cycle. That is called somebody calls it the ontogenetic change in the niche or niche shift. Okay, that's something that is rather common in fish, and you will find it in the sea for many, many species. So it's a candidate mechanism for bistability for many of the systems we study. Okay, we're going to look into it. It generates bistability if we start at low equilibrium abundance. So at low abundance, we end up at the low equilibrium abundance. And if we start at high abundance, we end up at the overcrowded state. And we're going to do it, and you will see that that's the case. If you want to find out what is the resilience, if you wish, on the one side of the two equilibria, but you also want to know where the tipping point is, and that's the red steeple line here. So if I want to tip off the system over to the low equilibrium state, I need to move beyond that line. And we're going to do it by simulation. We're going to find out, okay, how much should I reduce my population size to end up in the low equilibrium state? Okay, that's management action. Okay, this is the theoretical. We won't spend too much time on it, but that's the way essentially you summarize the properties of your system, or your model in this case. You have the juveniles, the adults. It turns out that when you draw what I call the zero net growth isocline, so they describe essentially that's the line, the blue line, for example, for the juvenile, shows the line at which the combination of densities of juvenile and adults generate a zero growth in the juvenile population. The red line shows the zero growth, the zero net growth isocline for the adults. And when they cross, neither the juvenile nor the adults increase or decrease in abundance. That means that's an equilibrium point. Okay, that's the one equilibrium point. That's the second equilibrium point. And I can study by simulation. I can put many starting points in this plot, see the trajectory, and they either here or here, and draw what I call the basins of attraction for the two equilibria. Okay, so I can start at any spot here, find out whether my trajectory, so the population will end up here or there eventually, and I can color code, for example, this story, and I will have an idea of the resilience of the two alternative equilibria. If the one equilibrium is resilient, it should have a very broad basin of attraction. Okay? If it has a very small basin of attraction, it's really easy to tip off the system over to the next equilibrium. That's the yes.
But if you don't My father was just push the enter. Yes, enter. Yeah, if the button enter.
What did our data?
You can fix it. For example.
Yeah. How did he fix it?
What?
What did he do to fix it? He took the two files and.
So we run the function.
That's a PDF. If you copy that.
Yeah, but like if you don't understand what's going on.
It's the top.
Yeah. So if we change that to say 200, it'll go twice as high.
Then I show you.
To see whether we meet.
That
A
means
name
it's the
called
parameter, right?
If you write, we manage.
Yeah. Well,
It's a short form for parameter.
here it says basically it says that we have this carrying
Okay.
capacity,
So we even
capacity
found
and the
by
growth
choice
rate,
there,
and it goes into a function
Okay.
called pounds.
solution of the spot
Basically, if we, I'll just do the first one, then you can do it after.
where you have this unstable.
If it's okay.
If you want to check whether indeed
So
that
if we do
equilibrium
like
is
this,
unstable, you just modify a little bit the starting condition. So rather than 1,
because I
you
want you
write
to continue.
1.1 or 0.9, and that should send it all the time away from a value of 1.
Use this.
So the trajectory should depart from 1. And that's something we can do if you want.
So now
We can in the
the
script.
whole lot.
So
Basically,
Sorry?
because we
if
didn't
your
get an error
abundance
message,
is above
it's
1, then
accepted.
you are
So
here
now we
and
have
it's
all
below
those
1.
in.
Yes,
If I write
yes, and
one,
we can experiment. So you can go in and you focus on the
the value
starting
is
condition.
started.
So
Basically,
essentially
make a column where 1 is
yeah.
the first
No,
is
no,
called K, it's called 100, R is
there.
called 0.5.
we can modify that, and let's say that we rather than dividing I by 2, you divide it by a small like 2.1 or something like
the
that.
rest, and now I'll do
Because then you change all the starting.
Again, we make a function called times. So like
Okay.
basically it gives us a function of time here. A sequence from 0 to 100 with a length of 100.
So then you run
Is it in hours? Is it in years? Is it in seconds?
That doesn't matter, it's a unit of time.